We're going to spend some time in the ozone. We're going to look at the properties of ozone and its effects on our lives. And here you're going to pause so that you can go down this checklist and mentally put a check by the ones you know well enough to explain to a friend, and then move on when you have done that. And here to pause again to look at the table to compare oxygen and ozone, why their boiling point's different, why their solubilities in water so different, with ozone being more soluble at 25 degrees Celsius compared to oxygen. And ozone and oxygen are allotropes, a substance with the same chemicals here and different structure. And compounds like calcium carbonate have the same molecular formula, and marble and chalk are going to have some different physical properties. And with carbon, with diamond and graphite, and fullerenes as well. And the bond order, look at the structures here. You're just describing the number of bonds between two atoms. And another table to pause on here and look at the difference in bond lengths. Why is the bond enthalpy, the bond strength, the amount of energy to break bond in ozone, less than that in oxygen? And here we're looking at the bond lengths. Multiple bonds are shorter than single bonds. So are the differences in the bond lengths that you see there expected in both oxygen and ozone? And here we're looking at formal charge. And for each atom, you're looking at the number of valence electrons, subtracting the number of lone pair of electrons, and subtracting half the bond pair electrons. And so you end up with a formal charge, which is in essence looking at a polarity of the molecule. So O3 is polar. What about oxygen? Work out the formal charge on an oxygen atom in O2. Pause to do that. And here, to look at ground level ozone. In the center section, you can read through about the harm that it does to our health. On the left, you've got a diagram showing ground level ozone compared to atmospheric ozone. And on the right, how ozone is formed in the ground at the ground level. And atmospheric ozone is part of the stratosphere. So the ozone itself probably goes from about 12 to 16 kilometers high in the from above ground level, and it's actually formed by UV light, energy on oxygen, forming free radicals, which then react with more oxygen to give ozone, and the free radicals can react with ozone to give you oxygen back. So constantly in the stratosphere, ozone is being made and is being broken down, but it leaves an amount that is there constantly. And then we've got the depletion of the ozone layer, often caused by halogen atoms and man's use of chlorofluorocarbons in refrigerants. In the high altitudes, high energy photons produce chlorine atoms which break down ozone. And when you get any free radicals as well with the ozone, it goes back to oxygen. And it's worth pausing here and looking at the URL that's given at the bottom right to see the change in the ozone level over decades. And then we have looking at the ozone hole. And you're looking at the graph on the right, and the horizontal line across it is the temperature at which you get polar stratospheric clouds over the Arctic and Antarctic. And there, once it goes below 78 degrees Celsius, the ice crystals in the clouds stop the formation of the ozone, and which is why you're going to get ozone holes being formed. Slightly less in the Arctic. The time span that the Arctic spends below 78 degrees Celsius is less than that in the Antarctic. And sometimes way south from the North Pole, north from the South Pole, with the polar vortex moving, you can see polar stratospheric clouds, even in non-Arctic, Antarctic areas. And different wavelengths break down ozone compared to oxygen. And it's all about the bond strength and the amount of energy in the different wavelengths. So higher energy is needed to break down the diatomic bond, and so UV light with a wavelength less than 242 nanometers, so higher energy, smaller wavelength equals Hc over lambda, for those who need to know that one. For ozone, it's lower energy, and UV light 330 nanometers, so a larger wavelength with a lower energy. And on the right you can read about free radicals, so pause to do that. And here we have a look at human activity and halocarbons, chlorofluorocarbons, refrigerants included, gives you some other uses of chemicals that are ozone depleters, and as the amount of that has increased, the ozone decreases. Now, you've gone through that, do another check off here. So you used to think, and having looked at this, now you think, which ones can you now describe better to a classmate? And what other ozone facts do you know that aren't covered there? So pause to do that one. And then some more things to think about, and indeed to explain. But the first three, looking at UVA, UVB, UVC wavelengths, and how much is absorbed by the ozone layers. And so those wavelengths, ultraviolet light that is harmful to our skin, etc., is prevented from reaching ground level when there's an effective ozone layer. And the questions below, so pause there to go over some of those questions. And another activity that you might want to work through, generating maps of ozone concentrations, etc., which go actually beyond ozone into other air quality considerations as well. And many thanks to Miss Hager and her 11th grade IB chemistry students. Very many thanks.